All right. Good morning, everyone. Still morning, right? 11 a.m. So I hope that everyone, I hope you have, already had your breakfast and you are doing well during this time, tough times. And today we are very happy to have our speakers with us to share their knowledge in FTIR. May I know how many of you have done FTIR before? You can press 1 on the chat box if you have done FTIR before. Could you please press 1? I just want to see. Or haven't done any FTIR, can press 2. That's good. So I think everyone must, like eager to learn about it. I didn't know any single thing about FTIR actually. So I'm looking forward to listen to what we have today. So welcome on board, everyone, fellow researchers, fellow lecturers, technicians, and students, okay? I hope you will enjoy the sessions and learn as much as you can. Please feel free to ask questions during the Q&A session we're going to have at the end of both talk, okay? And maybe it depends on the speaker as well if they do allow questions during their talk, okay? It depends on, you can actually ask them whether it is allowable to ask questions during their talk or not. So let me introduce the first speaker for today is Dr. Nurfatiha Ghazali. She is a lecturer from School of Dental Sciences, USM. Okay, she has been serving in USM for, I'm not sure, maybe like around four years again? Yeah, correct. It's 4 years roughly. So she graduated in 2017 with a PhD from UTM. Okay, her research interests in biomaterials, especially in development of biomaterials for a lot of things, a lot of applications. She has experience in handling high advanced instruments such as the FTIR, the UV-XRD, SEM, and also fluorescence microscopy, and many more. You can ask her later. And she has published her work in several journals. And she also has collaborators and grant from USM. And currently she is a member of MBS and also Persatuan Zeolite Malaysia. So I think without further ado, I would like to invite our first speaker of the day, Dr. Nurfatiha Ghazali. Please welcome on board.
Thank you very much, Dr. Nurhayat Yusof. Can all of you hear my voice clearly? All right. All right. Assalamualaikum, and a very, I'm not sure whether it's a good morning. I think almost to afternoon. Anyway, thank you to the chair, madam. Thank you to all. I think most of our audience here is from mostly is a student, I guess, postgrad student, undergrad, I don't know, and some of the lecturers. So for my presentation today, let me share my slide. Okay, can you see my slide? Right. So for today talks, I'm going to give basically on the fundamental, the principles, and I will touch also a bit on the preparation, sample preparation, but for the basic, because this is for the beginners, so not very deep, because I guess the second presenter, Dr. Oi, will touch more deeply on the instrument, right? So for the beginners of FTIR, mainly in my talk, this is the outline of the presentations. So I'm going to touch about a glimpse of Fourier transform infrared spectroscopy. So a little bit history of the FTIR, how it been invented from very, I think, 180 years ago to until now, 2021, and then a little bit part 2, sample preparation, as well as the characterization, and also the structure elucidation from the data interpretations. Okay, So the glimpse of Fourier transform infrared spectroscopy. So IR spectroscopy actually have been invented long time ago in 1800s years by Sir Frederick William. All right. So he have been invented this instrumentation based on the prism or grating using the monochromatomes. Right. So after that, this invitation have been continuously continued by Michelson using the interferometer in 881, where this interferometer is part of the instrument, and it continued by Peter Filgate, which he's the one who obtained IR spectrum by using FTIR spectrometer. And then the first commercialized FTIR spectrometers instrument in 1960s, and then followed by the Kulituki that developed a lot of thing modifications on the machine, which consists of algorithm, which also quickly does a Fourier transform. So this is how it looked like from the 1800s a year, where it only used the prism, and then it have a spectrum where consists of the blue, red, yellow color, and then it have the thermometer to check on the temperatures, and then it's only invented in the box. So this box with the white paper on the bottom with prism will create a possible spectrum. And then this FTIR instrument have been invented year by year, and it become more advanced. And for your information, it's not only has a very simple from the simple instrument, it can become a very high-end technology instrument, and it can be used to characterize many types of sample, right? So before we go any further, for the beginner, let we understand the term that used in the FTIR spectroscopy. Actually, there's a lot of term, but this is the basic one that when you encounter to use this FTIR, we will always come to say what is actually Fourier transform, what is IR spectroscopy. Okay, there's some people also get to confuse what is spectrometer, spectrophotometer. Okay, is it the Fourier transform spectrophotometer, or is it a Fourier transform spectrometer? All right, and then in this FTIR also, for the beginner, you need to know how does the fundamental, especially the part of the electromagnetic spectrum. So in this electromagnetic spectrum, where is the IR actually located in the electromagnetic radiation? And for the result, sometimes you always we always encounter when, for example, your supervisor or lecturer, let me see your result, your spectrum or spectra. So you should know whether you are presenting a spectrum or a spectra. So it's a different thing. It's a different thing between this spectrum and spectra. So Fourier transform actually is a mathematical process, or it's a formula that been used to translate the raw data, which is has an interferogram, into the actual spectrum. So this Fourier transform actually is been invented by some scientists in the mathematics formula, right? So it been applied in the FTIR. So infrared spectroscopy, or we call it IR, is actually is a method that trigger the molecular vibration. So if you are in a having a background chemistry or material, you should know what actually molecular vibration. I think this is very basic for all of you, but this is for those who are beginner, this is actually what is IR spectroscopy. Is a method of trigger molecular vibration to the irradiation with the infrared light. So infrared actually is a light. So it will give information about the presence or the absence of the certain functional group. Okay, so that functional group is actually come from your sample. So whether you have a carbonyl functional group, whether you have a alcohol carbonyl group, whether you have a you have a aldehyde or ketone group, that is in the functional group, right? So spectrometer actually is a measurement of the is a measure of the variation physical characteristic over the spectrum. So spectrometer actually not only have in the FTIR spectroscopy, it also part of the UV, it also part of the NMR spectroscopy. So this spectroscopy, they have the spectrometer. So what is the spectrometer actually do? It collect the information about the material based on the amount of infrared, visible or ultraviolet light of its project. Okay, so it's actually is a measurement technique in the instrument. Okay, so spectrophotometer is another part which related both actually in the spectrophotometer itself, it also have the spectrometer. So a spectrophotometer actually it is the term where the photo in this it have in any instrument that have a photo, that it will have a photo where it used to indicate this spectrometer to use quantitatively measure light intensity with the wavelength, right? Okay, sorry. So the electromagnetic spectrum. So what actually is the electromagnetic spectrum? So it composed of the various radiation where it contain different wavelength. All right. So which this type of radiant energy, it will range from the gamma ray to the X-ray via the visible light to radio wave. So I will show you what is actually the electromagnetic spectrum. Most of us sometimes we only just say electromagnetic field, electromagnetic spectrum, but actually do we really know what is actually the electromagnetic spectrum consists of, right? So the spectrum of spectra, as I mentioned before, spectra actually is a plural of spectrum. So if you are presenting your work in the slide or for the conference or for the paper, you should know whether the result that you put, the FTIR result you put is actually a spectra or a spectrum. So if a spectrum, if you have like 2 or 3 sample for the comparison, so that result you put in one spectrum, it should be called it a spectrum. But spectra is a result of the FTIR. If let's say you have 3 sample, you put different spectrum, it should call it a spectra. So for example, the figure 1 shows the spectra of A, spectra of B, spectra of C, right? So don't get confused with the both spectra and spectrum is a result, but only if the thing you put like 3 sample in one spectrum or 3 sample split it in 3 different sorry, the 3 samples put in one spectrum, or it can be divided into 3 spectra, right? So this is a so what is a infrared spectroscopy? So actually the term is the definition is IR spectroscopy is the interactions of matter, right? It's any part of the electromagnetic spectrum where it call it spectroscopy. So it's an instrument assisted study between the matter and the electromagnetic radiation of any range. So in this electromagnetic radiation, it was developed or invented by the scientists, where from the formula of the energy equivalent to the H Planck. This is a H Planck. It have the actually the H Planck. They have the exact formula lah. And then with the this is, we call it the frequency. So this is a formula. So if you see here the electromagnetic spectrum, this is the wave. Okay, it is a wave where it starts from the radio wave until the gamma ray. So this, how this related? It related between the wavelength and the energy as well as the frequency. So the wavelength show how large is the size of the radio wave, right? If you see here, it's more than I think it's more than billions of nanometers wavelength for the radio wave until it can become a very tiny of the gamma ray wavelength, which is 0.005 nanometers. And then when you have a large or long wavelength, is it you need a high energy? No. Much longer of much bigger of the radio wave or the wave, the energy is very low. But if you have a very high energy, short wavelength, you need a high energy. So this is how it explains the electromagnetic spectrum. All right. So higher frequency, shorter wavelength, high energy, but lower frequency, longer wavelength, and low energy. All right. So where is the IR actually located? So IR is located at the between the visible and the microwave. So here is the IR located where it have in this FTIR instrument, right? So it's the energy is between the longer and the short, and then still the wavelength is around 10 okay. Sorry, the molecular effect is the molecular vibration. All right. So what is actually FTIR? So FTIR is stand for the Fourier transform infrared, where it prefer the method of spectroscopy. If you can see here, this is the simple that explain what is happening in the FTIR instrument, where it have the source, and it have the source where it transmitted the light. All right, you have the samples. So some of the light will be absorbed, some of the light will be transmit. Where when the light transmit from through the sample, it will the result will show through the detector, where we can see in the computer or the part of the digital that we can see the result, where it come out in the wavelength versus the intensity, right? So IR radiation, it pass through the samples here, and then some of the IR radiation will absorb, as I said, and some pass through. So the result actually is like a fingerprint, where there's no two unique molecular structure produce the same IR. So this make the IR spectroscopy useful for several type of analysis, right? So what information that you can get from the FTIR? So it provide what kind of information it can provide. So it can identify the unknown material, all right? It can determine the quality or consistency of the sample, and it also can determine the amount of component in the mixture. So for example, if your sample, for example, the sample powder, if you not following the right procedure to prepare your sample powder, it might affect the concentration, and you analyze through the FTIR, the spectrum or the peak, which will not show the exactly from the reference that you refer. Okay, so that you have to be careful when you make the sample preparation. Okay, so now I would like to go to the second part, which is the sample preparation. Okay, what type of sample you can analyze? Okay, so what type of sample you can analyze? So in FTIR, there's a lot of technique of handling the samples. So they are more effective. So one of the technique technique that we use is transmission technique, which is more effective than other specific sample type. So in order to obtain the best quality spectrum of your sample, you need to know, and it's very important, which handling technique actually work best for your sample. So acquiring the spectral data possible will give you more confidence in your result. So excellent quality spectra you can obtain in many type of sample using the transmission technique. So transmission technique actually is one of the more effective lah. All right. So what this transmission technique can be used alone or in conjunction with accessory such as microscope. Such as microscope, and liquid or gas cell to analyze. So what are the sample type that it can be characterized or analyzed is organic powder, which it should be formed in a pellet or mold form, thermoplastic powder, soluble polymer, thin polymer film, okay, regular shape polymer with preparation, so irregular shape polymer, dark polymer, liquid gases. So this type of the sample type can be characterized using the FTIR, using the transmission technique. So the next that you need to know is the structure determination. So how do we know? For example, organic structure determination. So how do we know? How the atoms are connected? Is it a single bond? Is it the double bond? Is it a triple bond? So those things you need to revise back, all right? So what are the single bond? What are the double bond and what are the triple bond? This is a very basic one, especially for the chemist student, for the material student, even for the even physics also. You can find this information in the textbook of the organic. It have all those information at the beginning. What are the type of bond, right? So a bit advanced or a bit more than this bond is the functional group that exists in the molecule. So this functional group is from the group of the alcohol. This is how the alcohol look like, where it the hydrogen bonded to the oxygen bonded to the hydrogen, and the R might be the C, the carbon might be the another functional group, right? So this is the ketone. So you have the R and the R primary. So both also can be bonded to another functional group, or maybe from or also from the carbon or hydrogen. But as long you have as long you know the ketone, how it looks like, where the oxygen bonded double to the carbon, right? So it must be symmetric, all right? So the next is carboxylic acid. So carboxylic acid usually it's a bit different from the ketone, where the carbon double bond to oxygen to oxygen. So that's why carboxylic, if you want to write the formula, usually we have the COOH at the back of the formula, right? The chemical formula. So R is maybe from the functional, another functional group like ethana, methana, right? Those can be in the R, okay? So when you revise all those that structure determination, the functional group, when you know about that, then you will go for the theory or principle, how this functional group, when how this functional group in our sample, when we analyze, how it works inside the instrument. So upon radiation of the IR, certain bond will give a response to a vibrating faster. So this response actually can be detect and translate to a visual representation, where we call it a spectrum, okay? So this specific bond actually, it responds to absorb specific frequency. So for example, this is the simple diatomic molecule, where you can see here, it have two types of atom, maybe from the carbon or hydrogen, all right? So this covalent bond oscillate, where during the oscillation, it will actually it will vibrate to each other, okay? So it will come up with this kind of wave, right? So this you have to understand that when the greater the dipole moment change through the vibration, the more intense it will work in the electromagnetic field to generate, okay? So when this wave, when the wave of the IR encounter through the oscillating electromagnetic field, it generates this oscillating dipoles. It will give the same frequency to the two wave couple, and the IR light will absorb. So for example here, just now it vibrate by the diatomic molecule. So this is the IR light, where from the spectrometer, from the machine. So when it encounter both, it will give a twice of the amplitude. So it couple and it become a couple wave where it can be detected by the detector, right? So this is some of the example of the what are the bond vibration that you can encounter when you use the FTIR. Okay, basically that you need to know what is the stretch, bending. Okay, because this type of bond vibration actually is the one that give that present the spectrum of your that present the result of your spectrum. Okay, so how the stretching what is the stretch vibration? So stretch vibration is a vibration or oscillation along the line of the bond. So it give a kind of like going outside from the plane, right? So the asymmetric is like this kind of the vibration. So one come in, one come out. Okay. So for the bending, is a vibration or oscillation that not along the line of the bond. So basically there's a type of scissor vibration, rocking vibration, twist and back. So if it in plane, it have the scissor and rocking. So this is kind of scissor. When you use the scissor, you know how it move. And then for the rocking, if you use the what you call it, buoyan, so it rock kind of like this. All right. So our plane, it have a two type, whether it's twist and back. So the movement is almost the same, right? All right. So spectroscopy, as I mentioned previously, is study of spectral information. So basically, this is the simple one that you can understand it, the physical stimulus where the source, and it will the source of the light will irradiate the molecule, it gives the response and the detecting instrument. So the result will give a visual, mostly represent the spectrum. Okay, here I would like to show there's a two video how the solid preparation sample and the liquid. So I just go as far as I can to, and explain along with this video, right? Okay, this is for the solid sample preparation. Okay, so in the solid preparation, for the solid sample preparation, you need to have a mortar and pestle. Okay, this is where they call it mortar and pestle, where your solid sample, you need to grind using this mortar and pestle. All right. Beside that, you also need to know that you must have a equable pellet press, where this is a part of the FTIR sample preparation, and you also have the bowl press and the dice. So this is where you put your sample, solid sample, before you go for the next step, right? So the next step is, after you put your sample inside you put inside the equipellet press, you will put this pellet press in the manual hydraulic press, where you need to use this press to make your sample become a pellet, right? Okay, before you start to prepare your sample, please ensure that all the stuff or all the instruments or the capsule press should be cleaned neatly, all right? And it should be washed using the chloroform, or you also can use ethanol. But during my study, I always use the chloroform because once it easy to remove other, because you have to understand, when you use the FTIR, you are not using your only sample. Maybe it have done by previous people that using not the same sample. Okay, so you don't know what are the same sample, whether apa, it sometimes can affect to your result, right? Okay, so make sure you clean your your capsule press before you go for the next procedure to prepare your solid powder. Okay. All right. So the same thing also you need to clean is the mortar and pestle. So before you use it, there maybe some people have used it for their sample, and you also can use chloroform or ethanol and dry it with the tissue or maybe the kim white. So before you put your sample, okay? Okay. So here's the next step is you put some of the KBR. Usually they have prepared the KBR, and you mix well with your sample powder, and mix with the KBR and grind it. All right. And then after you grind, you will you make sure you fix first the pellet press, okay, before you want to do the manual hydraulic, and then insert the dies in the pellet press and transform the ground KBR with the sample inside the metal spatula, okay, using the metal spatula, okay. Actually, before you put you grind it with your sample, you need to grind the KBR first, because we need to check on the background, okay. There's this information I just add in, okay. So you need to run the KBR first to check on the background, and then secondly you add with your sample, grind it again, and then when you check the background is smooth, there's no other things, then you add with your sample, okay. So this is how you use the hydraulic, right? So transform the whole entity into the hydraulic press, and then you will use there's a SOP until what are the exact press that you need, because if too much of the pressure, it can break your pellet inside the pellet press, okay. Okay, so rotate the knob and counterclockwise to release the pressure after you have pressed, right? So you can bring out your pellet sample. Okay, so you can see here, this is the pellet that have been pressed into the hydraulic. Okay, you can remove the upper dies slowly. All right, so this is the pellet that you have pellet with the KBR disc, whether it's only KBR disc or whether you mix with your sample, look like, okay. So avoid using your hand, even though you use the glove, usually we use the forceps to transfer into the sample holder, right? So then open the program on the PC and perform the background scan first, and then you put your sample inside here, and then you can run, right? Okay. So the next one is the IR liquid sample preparation. So for the liquid sample, usually we use the sodium chloride pellet, where this is the equipment that you should know and have before you run the liquid sample preparation, right? So this is the sodium chloride pellet holder, the type 1. And then we have the type 2, and then the nut screw for the type 1 sample holder, right? Okay. So first, you need to take out the NaCl pellet from the oven, because you have to make sure it dry. And then as well, again, you need to clean and through using the chloroform and dry them with the tissue, okay? So use a dropper to, sorry. So you need use the dropper to dip 1 drop of a sample on top of the sodium chloride plate. Okay. And then use another sodium chloride plate to put on top of that and sandwich it using at the angle. Okay, so please ensure that when you put both together, no bubble inside you can see through the glass. Okay, it's actually a quartz. Usually this NaCl made from this quartz, so usually you can see clearly whether it have a bubble. So make sure it doesn't have a bubble because it also can affect on your result when you analyze using the FTIR. Okay. Then you can place it on the sample holder. All right. So actually this liquid sample preparation also, if your sample is a bit like sticky solid, even though it's a solid but it's a bit sticky, like very viscous, you also can use this method where you can use the liquid sample. Okay, it's not only liquid, that one that the one that like kind of solution, but the one that like sticky one also you can use, because I have experience using my sample sticky solid, and I have to use this method where is liquid sample preparation to analyze my sample. Okay, right? And then place in the sample holder, and then make sure you tighten the 3 screw, okay, so that it will not drop, because this NaCl glass quartz is very expensive and you need to take care very carefully. All right, that's why you have to make sure when you put in the sample holder, you have to tie it up, right? And then you can go for the next step to analyze. So the same thing, the sample holder is there, you just put another the sample holder of the liquid at the same place where the solid also where the solid sample you have used to analyze, and same procedure, just run the PC. All right. Okay, so that is the sample preparation. So the next one is the structure elucidation from the data interpretation. So before we go any further about this, you need to know your spectrum or spectra, what are the modes that you use. Okay, so there's two types, whether it's an absorption mode or transmission mode. So the absorption mode is actually basic plot transmitted or absorb, where it versus the intensity of the transmission. So once you run your sample, you will see the peak or the spectra, will come out, right? So you need to decide whether you need the absorption mode or the transmission mode. So first, the frequency appear in the x-axis. So this is the frequency where it will interpret or translate into wave numbers, right? And then the y-axis is the intensity. So usually intensity is from 0 to 100%. Okay, so if you need to check more, to zoom in, you can increase the intensity. If you just need to see a broad one of your result, you can decrease the intensity, right? So this is the transmission mode. Okay, so transmission mode also the same axis. You have the intensity and the frequency with number. The only thing is different. The transmission mode, you see your peak upside down, from the peak become upside down lah. Okay, so the absorption is kind of like this one. Okay, it's on the base. You have the base and the peak went up, but here the peak will went down. So usually this is the most common representation. So for my student, I always ask them, make sure that you will transfer your result from the Excel and plot it in the transmission mode. All right. Okay, so classification of the IR band. So in the IR band, basically, for the beginner, you have to know this. The IR band, it can classify, has a strong, medium, and weak. So usually, if you see in the paper journals or the books, handbook, they only will put the short term S, M, or W. So it depends on relatively intensity of the IR spectrum, right? So a strong band actually cover most of the y-axis, all right? So, so this is what I said. If you have a strong band that can cover from 0 to 100%, you can see clearly the peak come out. But if your sample is not enough, the concentration is very low, even though it's the same sample, it also strong, but it will come out very weak peaks. So that is where you need to increase a bit the intensity. So the maybe it will come until you can zoom in, not from 0 to 100%, for maybe from 45% to 100% of the intensity, right? But if you really follow the procedure to prepare your sample, your peak or your sample peaks, which should come out very clear in the spectrum, right? Okay, so the infrared band shape come in a various form. There's two most common, where it's a narrow or broad. So narrow band usually are thin and pointed like a dagger. So this is the sharp spike. This is the narrow band looks like a very sharp spike. However, for the broadband, it's a wide and smoother. So typically, the broadband is actually displayed by the alcohol group, right? Alcohol group where it have the OH bond. So beside the alcohol, it also can be found in the carboxylic acid. But how to differentiate it? You need to know the wave number, or the wave number where the peak located, right? Okay. You also need to know the infrared active bond. So not all covalent band actually can display in the IR pattern. Only the polar bond can do so. So this is referred to as IR active, right? So the intensity of the band actually depend on the magnitude of the dipole moment where it associated with the bond, okay? Strongly polar bonds such as carbonyl group will produce a very strong band. Medium polarity produce a medium band. Weak polar will produce a weak band, right? So what are the strong band? Is from the carbonyl group alcohol. For the medium, maybe the carbon bonding triple to the C triple bond to nitrogen, and the group from this from the another one is from the aldehyde, I guess, the where it have the C triple bond to CH group. Okay, but for this group, if it is not observable for the IR spectrum, right? Okay, so I would like to share with you some of the data interpretation. So how we are going to observe, how we are going to interpret the basic IR absorption range, basic IR data. Okay, so typically IR absorption range is from 600 to 4,000 with number. But actually, if the new machine, you can see from 400 to 4,000. So for there's some instrument still, but still you can change actually the absorption rate, whether you want to see from 400 or 600. It depends on the machine, right? So the graph show the region of the spectrum where it following the type of bond. So this normally the OH, NH, and CH bond. Where bond to hydrogen, the triple bond or double bond is at the center from the 2,700 to 1,600, and the single bond fingerprint region is from I think from 1,600 or maybe 1,500 to 600 with number. Okay, so so this region actually you also can call it a fingerprint region, all right? So this is the normal complex area showing many band and frequently overlapping, but some of the complex also can be overlapped to each other, right? So however, for example, in this data, they study for the inorganic compound that usually observe of TiO2, okay? Okay, this is some of the table that that you can find in the textbook or in the journal. Sometimes they put how you want to interpret your sample that have a functional group. So you can see here when you run the sample, okay, for example, there's a peak come out at this region, okay, at this region. So where you have to look whether it's a medium or it's a strong. So if it's strong, means that in your sample they have a CH group, CH stretching. Okay, so it form alkane. Okay, the most important that you need to know from your sample is the main functional group. Okay, for example, in pyrazole, for example, in the pyrazole ligand and pyrazole complex in my sample. So in ligand, it will bond to an H, but in the complex, the H is no more bonded to the N, it's only N. So the NH region shouldn't come out in the complex spectrum. So that is how you interpret your data. So this characteristic absorption peak, these are the things that you need when you want to interpret your data spectrum or spectrum, right? So it consists of the alkane, alkene, alcohol, aromatic compound. So this is the basic one lah. The usually functional group that come up. Usually they give that they have. But if you have a specific functional group in your sample, you need to refer to a paper who have done the characterized using the FTIR. You also can match whether you get almost the same or similar of the data from the paper or the journal that have been published. Okay, there's some of the group that I will share with you. So for example, octane. So octane, or we call it octana or octana in Malay or octane in English, all right? So it only have a one single bond. So what are the important of this octane? It have the C bonded to 3 hydrogen, right? So it must have a C stretches where at the this is the C stretches to C, okay, where this should come out to the region at 1300 to 1470, and then it also have the CH2 double to CH2, where this is the located of CH2 double to CH2, and this will come out at the region 1450 and 1470. So it is between this. That's why they give the region or the wave number at certain, not the exact number like 1450. You must get this 100. No, sometimes you will get 1451, maybe 56, maybe 1460. So that kind of that region you should that region you should observe for your data. Okay, and then what else? You should have CH2 double bond to CH3. So this is the carbon that or the functional group that have the C bond to CH3. So this is the region of the wave number to come out of your peak. And then you have the sp3 CH between the 2800 and 3000. So this is the important one that you should see. If this peak didn't come out in your data, means that something wrong. Maybe you have to check back the concentration, the preparation, and maybe there's impurities. That are the thing you have to know. Okay. Okay, this is the second one, alkene, where it have a double bond of C double bond, right? So C double bond stretch at 1600. How do I know? You can refer from the table 1620 to 1680. So usually the peak is bigger as the substitution increase, right? So the most important is you need to have in your data is the vinyl. So usually, even though it's a big, but as long it come up another sharp, as long it come up in the spectra or spectrum, the weak or medium peak here at the range 3000 to 3100 means that you get the sample, means that you have successfully get your peak analyzed using the FTIR. So the third one is the alkyne, where it have the triple bond. So alkyne maybe is a bit different because it have a triple bond C. Okay, so where it located, this C double bond C, C triple bond C is at the region of 2200 and 2000, right? So this is the C triple bond C stretching, right? So it's an asymmetry, strongest for the terminal alkyne and weakest for the symmetrical internal alkyne, right? Okay, for the alcohol, is very, alcohol is one of the functional group is easy to see when you have in your sample. Why? Because if we come up with a strong, broad OH, where it stretched at the 3200 to 3400, all right? So if let's say you have another one is C bond to oxygen, it will stretch at the 1000. So these are the things that you need to refer to the table or the journal that maybe have a same functional group with you, right? Okay, this is the aromatic. Let's say your sample have the aromatic. So usually aromatic from the hexane, right? Or maybe the carbon in the aromatic group, right? So how to look where this aromatic group region in the spectra or spectrum, it will located at the 1600 to 1400. So because previously they have run only this aromatic group, and and if you want to make a comparison, maybe you have a sample that have another functional group here. As long this peak come out in your data, means that you have the aromatic in your sample. Okay, what are the things that you should know? IR group analysis is the primary use of the IR is to detect functional group. However, at the interaction of the EM spectrum with actual bond, it provides unique quality prop into the functionality of a molecule as a functional group and merely different configuration of different type of bond. But please remember, IR spectroscopy or FTIR did not or does not provide a detailed information or proof of molecular formula of structure. So for example, you have a sample, usually this for the natural product, they have a sample or that they extract, let's say from the anything, but they want to confirm that they get this the sample. You cannot depend only on the data of the FTIR. You have to do at least to confirm. You have to mesh. You have to tally with the NMR. You have to at least NMR FTIR. And another one is you have to check on the you have to check on the I forget. There's another one where you that one is mass spec of the sample where you can confirm. So at least these three instrument can help to confirm your sample whether you get or not, if you don't know what are the sample you extract. So FTIR usually what are the interaction. For example, in the hydrogel they have the OH group, they have a COO, they have the CH, so we know. But the thing is that why we use FTIR, we just want to confirm when we prepare we get or not this sample. Okay, so again, therefore it's very limited in scope that must be used in conjunction with other techniques to provide more complete picture of the molecular structure. As I mentioned, the NMR Yeah, another one is mass spec lah. The one that for example, you doesn't know what are your sample. You want to confirm, for example, natural product, you need to use the FTIR, NMR, and the mass spec, and also UV if it can run under UV, right? So I think that's all from me. Thank you very much. I'm sorry if some of the information is not clear, or maybe you need to ask something. Maybe at the end of the presentation, the second presentation, we can discuss. And thank you very much to attend to the talk. So hopefully for the next, I will improve more on the presentation. All right. Thank you very much.
Thank you very much, Dr. Fatiha, for the sharing. I'm not sure whether they do have questions. If you do have question, you can jot down or you can write in the chat box. Okay, Dr. Fatiha will stay until the end of the second talk. Okay.
All right. Thank you.
Right. So we need to move on with the second talk. Okay. Our next presenter for today is very special. He comes from Kedah, but I think he now works in KL. Am I correct?
Yep. Hi, morning everyone.
Hold on, let me introduce you first. Okay. He joined us today as the material characterization and senior product specialist from Perkin Elmer. He obtained his PhD in 2016 from UTM. His research interest is in nanotechnology, material sciences, and solid acid, and many more actually, but I just list down three. He has published his research in various journals and also involved in filing few patents for catalyst support material. Am I correct?
Yes.
Yeah, so please welcome our speaker for the second part, and give a big applause for the speaker, Dr. Oi Yi Kai.
Yep. Thanks, doctor. So I'll just share my screen. Can you guys see the screen?
Yes, Dr. Oi.
Okay, so as what Dr. Fatiha mentioned just now, so FTIR, the full name is Fourier Transform Infrared. Okay, so what is actually Fourier transform? So it's a mathematical algorithm that transfer the light signals from your infrared into the spectrum or the spectra that you can read. Okay, so I will not go through the theory again. Okay, but the important parts in IR that you should have some rough ideas, and I'll be focusing more on the application or what you can actually do with FTIR. Okay. Now, so I mean, this is the presentation that we covered. Okay, the one that we have covered just now, okay, or Dr. Fatiha covered just now, is the sampling techniques using the transmission method. So in IR, there's actually two, or in spectroscopy, there's generally two techniques that you can do samplings. One is the transmission method, another is the reflectance method. Since the transmission method has been covered, I'll be focusing on the reflectance method or the accessories required for you to perform your analysis. Okay, so infrared spectroscopy, okay, is important technique in organic chemistry. So how do you categorize organic? A very general rule of thumb is, as long as your sample contains atoms such as C, H, N, S, and O, so this is the things that we consider organic. Okay, but in reality or in actuality, FTIR actually detects covalent bonding. That means electron sharing between the two bonds. Hence, all that examples that have been shown previously, you can see that electron has been shared and then bonding has been formed. So regardless of, thus you can also do inorganics as well. For example, like what mentioned previously, titanium dioxide, TiO2. Okay, so glass you can also detect, for example, quartz SiO2. So you can also use FTIR. So as long as it's a covalently bonded, then you can do that. So that is precisely why for all the optics in FTIR, okay, or for the transmission example shown just now, the KBR method, where you press using the hydraulic press to form a pellet, that you have to mix with a metallic salt. A good example is KBr, potassium bromide. Okay, so that because KBr doesn't absorb IR. So that is why it can be used as a carrier, and it can be used to form the pellet for solid transmission methods. Okay, so as we have covered just now, for IR, the main purpose is to do identifications of the functional groups. So we can do peak designations and for the corresponding functional groups. And you can find the functional group tables readily available in on any websites, okay, or in the search engines basically. So it's basically for the confirmations of the identities of the compound, or to detect the presence of impurities or contaminants within your samples. So this is a spectra that we mentioned. So each peak that you have observed here is corresponding to different functional groups. Okay, so that is why we can say that, okay, based on the electronegativity of the atoms, the dipole moment will be generated once it absorbs the infrared, and then spectra will be generated. Okay, but of course later I'm going to show you how you can actually coming from the light signals to get the spectrum. Okay, so the main purpose is for the identifications of the molecular compositions for many organic and inorganic materials. Okay, so as mentioned by Dr. Fateha just now, below 1,600 wave number or 1,600 Cm-1, that is what we consider as fingerprint region, and that is the very important region for identification purposes. So these are the vibrational modes. Okay, you have the symmetric, asymmetric stretch, and then rocking, wagging, scissoring, and another one is the bending. So typically what you will find is stretching and also the bending modes for the molecular vibrations of different atoms or different bondings or molecular vibrations. Okay, so fingerprint regions is correlate to functional groups below 1,600 wave number. So in FTIR, okay, because in spectroscopy actually there's two techniques. Initially is first starts off in dispersive technique, which inside your spectrophotometer, you have a monochromator and a grating systems. The dispersive technique means using the prism, it will cut the light into the specific wavelength. And hence the unit is typically in nanometer. However, as the technology progresses, FTIR actually we are using interferometer where there is no monochromator and grating system inside. So that is precisely why in FTIR you will always get a spectrum. Okay, you can't do a single wavelength analysis unlike UV. UV still based on dispersive or grating systems. Okay, so in FTIR, normally as representation of the wavelength units, we are using Cm-1, but this is interchangeable. You can convert it into nanometer or Cm-1. Okay, so this is the wavelength. Okay, so this is the electromagnetic spectrum. I'm not going into detail about this. So a very important equation is the Planck's equation, E equals h c over lambda. H and c is actually the constant. So h is Planck's constant. This is the units, the wave values of it, and c is the speed of light. And lambda is the wavelength, which you substitute based on. So in IR, okay, for today's presentation, we are focusing on the mid-IR region, which in terms of Cm-1 is from 4,000 to 400, okay? But actually you have near-IR, which is closer to the visible regions and is from 15,000 down to 4,000, and below 400 to 30, okay, is far IR, what we call it as, and this is the complementary technique of NIR and near IR and mid IR. So if your sample is metallic, is ionic bonded, you can use far IR for the detection of the peaks. Okay, so this is a complementary techniques for the mid and the near IR. Okay, so IR is safe because it's just causing you molecular vibrations. As you can see from here, it doesn't cause any electronic excitations. Okay, and unlike UV, hence you do not stare directly into UV light because it's going to cause valence electron excitations. Of course, as you progress towards the left, X-ray, gamma, these are all radioactives. It's going to cause cellular mutations. And that is precisely why each year X-ray you can only do twice. Gamma is fully radioactive. You do not want to expose yourself to that because it's going to cause SP shell electron excitations. Okay, so E equals C over lambda. So C over lambda is HF frequency. So as you go across, the frequency will be increased higher and higher. Means wavelength shorter, higher frequency, higher energy. Okay. So important parts in FTIR or in the modern FTIR, you will have source to generate the infrared beam. Okay. Regardless of what are the ranges you are using. So different ranges of IR, you have different sources to generate it at different wavelength. In the terms of mid IR, we are using silica carbide. Okay, so it's a heating element. So it's going to heat up and then generate a infrared beam, okay, or light, infrared light, okay, if you will. So a very important part in FTIR is the interferometer, and this is the part where it converts the infrared signals into the electronic signals or the spectrum that you can actually read, okay. And then we have lasers, okay, the helium neon lasers. This is a high performance laser, you acting as a internal reference to make sure your abscissa accuracy and precision. That means your wave number is accurate. How are you going to make sure that when you scan 4,000 is 4,000, 3,000 is 3,000? It all depends on the internal calibrations from the lasers. Okay, of course, detectors will have different detectors suited to different applications or different sensitivity levels. So most common one you will see is the temperature stabilized DDGS. You have lithium tantalate, you have MCT, you have different types of, if budget allows, you can go for the highest end, for example, the QCL. Okay, so different detectors, different sensitivity levels, but typically for DTGS is more than enough to cover most of the applications. So as I mentioned, IR, you have different ranges, and in Perkin Elmer, we actually covers in one instrument. So you can see here, we cover all full tri-range. So near, mid, and also far, we inside the single instruments. Okay, of course, you can opt for, the most conventional IR, FTIR is the mid IR, of course. So people do use near IR as well, especially for those dealing with drugs, pharmas, or pure or food products, basically. Okay, and then if you have a lot of metallic samples or ionic materials, then 4IR is required as well. Okay, so this is the sources. So Perkin Elmer, we are not new in developing IR. We actually started since World War II. So we have a lot of patented technology to ensure the sensitivity and the performance of the FTIR. One of it is the stabilizer sources. Okay, so this is what we call as hotspot stabilization. So this is the heating coil. So this is the silica carbide heating element. So during generate the IR, the heating coil will heat up, and then we are make sure with this design we can ensure the maximum output of the infrared beam and is consistent and maximum output of the infrared reaching your samples. So to reduce the noise, reduce the baseline drift, and also to increase the signal to noise ratio. Okay, and of course the conventional heating element is only from one-sided, and this over the period is going to causing the loss of energy, leading to more noises and less sensitivity, hence the poor quality data quality. So in IR, you want to achieve the higher signal to noise ratio. Of course, in terms of software, there are other things that can do, but all these are from the hardware complementary. So interferometer, this is the simplified version of it. So within the interferometer, actually you have the moving mirror, fixed mirror, beam splitter. This is the conventional Michelson interferometers. So source generate your infrared beam, hits beam splitter, going to moving mirror, going to fixed mirror, recombine at beam splitter, going to detectors. So all this is light signals, okay? That means it's a cumulative of all the wavelength. And how are we determining what's the wavelength that we're scanning at the moment? Is determined based on your moving mirrors, okay? So this is how we, okay, and in Perkin Elmer, we are actually coming up with a patented design of the interferometer as well. It's called Dynascan interferometer compared to the conventional Michelson, where the mirror itself is moving. Okay, when mirror itself is moving, you have the risk of tilting and shearing. That means the mirror position is out of alignment. Okay, if the mirror itself is moving. So this will cause that wave number readings to shift, whether it's a red shift or it's a blue shift, is going to cause a shift nevertheless. And in terms of IR, since we are going to use spectrum for identifications, you do not want any wavelength shift or wave number shift, because for every 5 wave number shift, we consider it as a different functional groups. Okay, so in this design, the scan pair acts as a moving mirror. So you have 2 mirrors here. The moving mirror, fixed mirror will always be fixed at a certain positions. And down at the scan pair, there's a heavy metal plate, which is going to move at different wavelength. So the mirror position is static. What is controlling the light path length is actually being controlled by the heavy metal base plates down below the scan pair. And this will minimize the tilt and shear effect coming from the mirror movement, since there's no movement at this moment. Okay, so the scanning principles is when we control the wavelength, how we control the wavelength, or we control the path length, the light travels, the infrared travels, if you will. Okay, so we can either decrease path or increase path. As you can see, the mirror position of the scan pair is always the same. So based on the base plate movement, we control the light travel path length. So how does light travel? As we call it wavelength, that means it's going to travel in a sinusoidal form. Okay, of course, in terms of light, is a wave particle duality. In IR or FTIR, to be specific, we call it as we are referring to macro chemistry. Okay, if you are referring to quantum chemistry in terms of light, you are referring to the particle qualities or the particle characteristics of the lights. Okay, but in macro chemistry, light travels in wavelength, hence is a sinusoidal movement. Okay, when your moving mirror and your fixed mirror distance is the same, we call it as a constructive signal. So you get this, and once the travel distance is different compared with fixed mirror, okay, then you get the destructive signals. So as I mentioned, this will control your wave number. So all the light signals combined at different wavelengths, you will get this is what we call as a interferogram. So interferogram is not a spectrum that you can read. Okay, a readable spectrum here will be either absorbance or percent transmittance, and here the x-axis will be the wave number. Okay, as you can see, this is energy and this is Mahalanobis distance. This is what we call as interferogram. And from this interferogram, we are converting it using that, and this is precisely why it's called FTIR, going through a mathematical algorithm. Okay, and now you have a spectrum that you can read. Now you see that this is Cm-1 is a wave number unit. Okay, so this is a mathematical this is all just the principle how you get the final spectrum that you can read. So as a user, you once you perform a scans, it will directly gives you the spectrum. And IR is a ratio technique. So good practice is you should scan a background before you scan your samples for each sample that you want to perform. And since it's a ratio technique, at every wave number, the signals will be ratio against background, and the end spectrum that is corresponding, it will only comes from your samples only. So we have removed the interference from the background. Okay, so all modern FTIR is actually FT. Now you hardly see any dispersive IR anymore. Okay, so how do we increase the signal to noise? As I mentioned, we want to achieve the higher signals to the lowest noise. Okay, so we can, since signal to noise is equals to square root of number of scans, so we increase the number of scans. For general applications, whether you're scanning solids or liquids, typically 16 number of scans is more than enough. Means at 16 scans, your sample is going to be bombarded 16 times by the infrared beam. And this can actually provide you quite an optimum signal at the shortest amount of time. So normally for the sufficient number of scans, we can just use 16. And another thing that you need to control in your IR, or you can optimize in your IR, is the resolution. As I mentioned, the mirror movement here is referring to the moving mirror. Okay, so generally we are setting it to 4 Ci-1 for resolution. Okay, what does it mean here is if you set the resolution to a low resolution, your mirror has to move from the default position 0.5, and this couples with your number of scans. That means if I say 16 resolution 1 cm minus 1, your mirror has to move 0.5 cm 16 times. Means go back to default position, move 0.5, default 0.5. Okay, so if you set the resolution to very low, it's going to take a very long time to perform a scan. This is what we call as the optical path differences, or the moving mirror difference, the movement. So generally 4 cm minus 1 is good enough. Okay, so if you have gas sample, of course you need to scan it lower because it's dynamic, and generally the absorbance is not that have a weak absorbance. So typically we use a lower resolutions. So if your sample generate a very weak signals, then you need to go for a lower resolution. But typically for most of the application, 4 is more than enough. Okay, so these are the advantages of FTIR. So as I mentioned, no monochromator, no slits, so better energy output, better signal to noise at any given resolutions using the helium neon wave laser to calculate your band positions or your wave numbers to make sure your abscissa accuracy and stability. And zero stray light and immune to room light because it's based on ratio. So all the light signals from your room light or the stray light will be ratio off during the background scans. Okay, and inside that there's only one moving part, hence reducing the tilt and shear effects and also the wear and tear effects of the moving parts as well. Okay, and as I mentioned, all frequencies are measured simultaneously. So in IR, there will be no single wavelength measurement, unlike UVVs, for those familiar with UVVs. Okay, because if you're familiar with UV, you can monitor absorbance at certain wavelength. For example, 580 nanometers. But in FTIR, we measure all wavelength because we are converting all the cumulative light signals into the spectrum that you can read. So in IR, you will always get a spectrum. Okay. So this is the sampling techniques. Okay, in terms of sampling techniques in spectroscopy, we are referring it to transmission and reflectance. Okay, so transmission means the infrared directly hits your samples. What is not being absorbed is being directly transmitted. So solids, you have your nozzle mill. This is a very conventional technique. We have the where the samples need to mix with a nozzle oil and then sandwich between two metal salt windows. Okay, and then scan directly hits your samples like what Dr. Fatiha shown just now. And then if you mix it with the KBR powder, then you press it into a pellet using the hydraulic press. Okay, so liquid, you can run all this, and then normally the liquid cell is required. Okay, and gases, of course, gas is always transmission. Okay, you need to collect your gas samples within a gas cells. So gases is, so in IR, we always categorize it as the versatility of the sampling tools. So choose the correct sampling tools to get the best results or the best spectrum that you can get. Okay, so these are some of the factors that you should consider when you're choosing your sampling techniques. For example, your sample thickness, the particle sizes of it, refractive index. Okay, if your sample is very thick, has a very high refractive index, transmission might not be a suitable tools to, or the transmission might not be a suitable mode to run your samples. So we have reflections. Okay, so diffuse reflection is, so all these require a very specific accessories, okay, which FDR caters. So diffuse reflection is for sample that is matte, is coarse. For example, like your painting, your coatings, your catalysts, your powders. Okay, sample that tend to scatter a lot of lights, then you can use diffuse reflections. Then the most commonly readily available or the universal technique now is what we call as ATR, is a single bounce reflectance technique, or what we call as attenuated total reflectance. Okay, this is what I'm going to show you, and we are focusing more on this. And as for specular reflection, this is for a sample that's highly polished, highly reflective. Okay, so that typically is for like metallic samples, which your angle of incidence and your angle of reflection is the same. So this is sample dependent, is a quite a niche accessories. Okay, so traditional sampling technique. So if transmission means you slot your sample holder in the infrared pathway, or this is what I call as a sampling compartment. Infrared will pass through. So it will hit your sample directly and goes to detector. Detector is over here. Okay, so transmission regardless of what accessories you are using, whether it's for solid, it's for liquid, it's for gases, is all transmission, means directly passing through your samples. So this is the KBR this or for KBR transmission method for solids. So the ratio is 1 to 100. If you're using, like, for example, 1 milligram of samples, you mix with 100 milligrams of KBR powders. And why we use potassium bromide is because it is metallic, it is ionic bonding, so it does not absorb mid-IR. So it's a suitable carrier to carry your samples. In fact, the optics within your IR is all made from KBRs as well. And that is precisely why IR, we do not switch it off, and humidity, you must control your humidity because KBR is hygroscopic, it tends to absorb moisture. So you do not want your optics to have fogging issues. You need to maintain your environment at a specific humidity less than 65% RH if possible. Okay, so the palette just now usually is the 13 mm. Of course, you can have the hand press. For a smaller palette sizes, it's the 7 mm. So this is the configurations or the accessories you will require for you to generate a KBR palette or the solid transmission methods, okay, as shown by Dr. Fatiha just now. So if it's liquid, if you can you can evaporate the solvents and cast it into a film. This is what I call as the cast film techniques. You can directly measure the films after the solvent evaporated. But what if your sample is highly liquidy? It does not form any films, okay, or it contains a lot of solvents, then liquid cell will be is generally recommended. So this is a liquid sampling tools, or what we call as a liquid cell. So this is what we call as the salt windows. It's not glasses. It's made from salt windows, different types of materials. Typically, it's KBR, potassium bromide as well. As I mentioned, it does not absorb mid-IR. So it's a good windows material for you to choose from. So light directly pass through. This is how you assembled it. Okay. So how you do a sampling of liquid sample is you inject your sample from here, and then it will form a thin film in the spacer here, and then the excess will flow out. Thus, it's still a transmission technique because light directly pass through as well. So if your sample is non-aqueous or non-polar, you can use KBR. Okay, but let's say your sample contains a lot of moisture or it's a water-based samples, then you can use other types of windows material, for example, like barium fluoride. Okay, so this is how it looks when it's being assembled. Okay, the spacer is controlling the path length. Okay, for those familiar with Beer-Lambert's law, absorbance equals to epsilon BC. Okay, if you are using UVs for path length, we are controlling by the cuvettes. Okay, but in IR, the liquid cell, this spacer in different thickness is what controlling your path length. Okay, means how long the light travels. Okay, so for liquid samples, okay, based on the Beer-Lambert's law, okay, we want to increase the absorbance for low signals, for examples. So what if you cannot adjust your concentrations? Typically, what we do is we adjust concentration if it's allowed, but if not, then you adjust your path length. Okay, so if in UV you can use a large cuvette, like for example 50 mm or 100 mm cuvette to increase the absorbance. But for if IR, we can use different thickness of the spacer. So you can see these are referring to the spacer thickness. So if your sample contains a lot of or highly concentrated, you use the smallest path length because you do not want to saturate your detectors. Okay, that means you're going to get a cut-off peak instead of a full resolve peaks. Okay, so if you have a very low concentration, which typically has a very low absorbance, then we increase the spacer path length so that we can increase the signals. Okay. So these are different windows material for different types of applications. For general purposes, is potassium bromide. If for those dealing with petrochemicals, okay, then you can go for zinc selenide for non-polar materials, okay, for oil samples or for petrochemical samples. Then this is gas cells. This is the shortest path length gas cells, 10 cm gas cells. So you need to trap your gas within the gas chamber, and then gas will definitely or will always be transmission. There's no reflectance for gas. Okay, so all these methods that I've covered just now is for transmission, regardless is liquid, solids, Okay, so if solid is KBR, if liquid is the liquid cell. And now this is the gas cell for gas samples. So ATR, okay, ATR is the most versatile sampling techniques. Okay, not to say it replaces, but it can be offered as an alternative for your KBR methods or the liquid transmission cells just now. And it can basically, or it can analyze practically anything that you can put on top of the crystals. Okay, so liquid, pastes, powders, solids. Okay, you can just analyze using ATR. So this is what the working principles of ATR. So you put a sample on top of the crystals. The infrared comes from below. Reach your samples, sample will absorb. Okay, and the absorbed infrared will be released as an evanescence wave, and then most of the light will be reflected and goes into the detector. Thus, it's called the reflectance technique. Okay, ATR, attenuated total reflectance, and ATR is a surface analysis or a surface technique because the penetration into the samples is only 2 microns. Okay, generally it's 2 microns. Of course, with different types of crystals that you choose, the penetration depth will be different, as I will show you the examples later. Okay, so this is the formula used for the calculations of the penetrations into the samples. Okay, so if you are running solids, means it must be in direct contact with the crystals. Crystals can be different types. The most common one is the diamond crystals. Okay, of course you can have like zinc selenide, germanium for different applications as well. So one very important parameters or criteria that you have to bear in mind when you choose your crystals is what is the refractive index you're going for. Okay. So factors to consider: refractive index, chemical compatibility, whether the crystals, what does it react with polar or non-polar ionic or acid bases. So these are the things that you need to consider as well. You do not want to have a corrosion happening on your crystals. What is the range? Because different crystals have different cut-off ranges. And what is the mechanical strength? How robust is the crystals? Okay. So these are the type of crystals that we offer. So for diamond, okay, diamond is the most versatile crystals, okay, and it has the closest Ri base closest to the environment or to the air, which is 1. Okay, germanium has 4 Ri, okay, and why we need this? The higher Ri you have, the shallower the depth of penetration, means the infrared actually hits your sample at the lower angles. Okay, so most of the light is still being reflected. So germanium is good for dark color samples or samples that tend to absorb a lot of IR. For examples, graphite, graphene, okay, or CNT, carbon nanotube. Okay, but the trade-off is it only scans down to 780 wave number. That means below this, you will only get noises. And germanium is fully metals, so you do not run acid or base or highly ionic materials, highly ionizable species, because it will react. Okay, so zinc selenide is good for oil sample petrochemical applications generally. So if you do not have any specific criteria to choose from, we always go with diamond, because diamond has the widest transmission range, means it covers the full IR range, 4,000 to 400, and the depth of penetration is around 2. Okay, and it does not react, it's inert. Diamond is inert, so you can run acid bases, ionic species, and the most important thing is it's highly robust. Okay, that means it's anti-scratch, so typically you wouldn't damage your crystals. Okay, so sampling is non-destructive, directly placed down, and if solid, you just apply pressures onto it. If it's liquid, you can just drop on top of the crystals. Okay, so this is the pressure gauge to apply pressure onto your samples. As I mentioned, infrared comes from the sources, hits your samples, reflect, goes into the detector. Okay, and ATR is a single bounce. That means it's going to hit your sample one time and goes to detector. So depend on number of scans that you set, it will repeat this process for the settings that you have set. So solids, Crystals is only about 3 mm, so you do not need to cover the whole metal plate. This is the metallic through plate. It's fully sealed. That's why you can run liquid samples. It will not seep through. Okay, so solid directly press using the pressure gauge. Make sure that it has a good contact with your crystals. Okay, so fully cover the crystals, then you can do a scans. So examples, this is a urea granule. Okay, so this is generated the spectral generated from the ATR accessories. Okay, we directly put on top of the crystals, and then we just do a scan. Okay, so if liquid, can just drop one drop on top here, then you can just scan without need to apply, because most of the liquid have certain wettability index, then it will spread out just nice and cover the crystals. Okay, so as I mentioned, diffuse reflectance is a specific accessory. It looks like this. So it's good for scattering materials. Okay, so for example, like food, soap powders, coal, clay, soil, papers, painted surface, polymer, and catalysts. Okay, so you can have diffuse reflectance or sample with very high RI, refractive index. Okay, next is the software features. Okay, so most important thing in IR is for identifications, okay, of the spatial configurations of your materials or the molecular compositions of your materials. So everything is in one page. This is the software we are using in Perkin Elmer. We call it Spectrum IR. And okay, in the software itself, we have some patented features as well in the software. So it's to help to get a better data representations. For one example is AVC, atmospheric vapor compensation, where the software will auto recognize whether the moisture, okay, this is from the surroundings. Typically, you will have all these interferences. Okay, so this is moisture stretch, moisture band, this is carbon dioxide, okay, and this is CH, or from the organic matters or the volatile matters. Okay, so from the AVC features, atmospheric vapor compensations, the software can actually eliminate the interference from the surroundings, the moisture. And the software is intelligent enough that it only removes the moisture and the carbon dioxide from the surroundings without affecting your interstitial moisture, for example, interstitial OH. So for example, samples like carboxylic acids or alcohols, the OH will still be present, or your sample is water-based, OH is still present. It will not be removed. It only removes the background interferences based on the AVC features. And this is automatically done or automatically performed for each of the scans that you are running. Okay, we have scandalized, means after you scan, you want to do a compare. Compare means you are doing a quality control, basically. So you have a reference spectrum, then you have a samples that you want to compare with the reference spectrum. So where you apply this is, for examples, for those doing organic synthesis. Okay, so you have a very successful synthesis, for examples, that you are sure that this is the spectrum that you want. So you keep that as your reference. And for the next batch of synthesis, for examples, you want to see whether the sample is the same. So you compare in terms of spectral quality. Then you can use the compare features. Okay, so we use the correlation, means how similar it is, and we set the pass-fail criteria. Okay, you can set the sample spectrum must match with your reference spectrum in terms of how much correlations. Like for example, 0.99, 1 is fully similar, so we normally don't set it to 1. So you can set like 0.98. So it must achieve these correlation levels before it considered pass. That means it has the same functional group, same spectral quality. Okay, so you can use this as a quality control tools or for compare features between your reference and your samples. Okay, next is the library search. Okay, in IR, beside the peak designation that we've been shown previously, okay, that is the manual way, whether you do a literature review or you search based on the spectrum tables or the functional group tables. Another way that you can do for identification of unknown materials is using the library search. Okay, so libraries, you can either generate your own libraries based on the scan spectrum You can create your own libraries, or you can actually purchase the third party or the commercial libraries readily available. Okay, regardless it's NIST or Bio-Rad, Setzler, they have FTIR libraries for identification purposes. Means you use the search functions, it will tell you based on the matching what might be the potential component or the compound it is. Okay, so search. For example, I have samples that I scan. Okay, I'm not sure what it is, it's unknown. Then I'm using the library search functions. It tells me that it matches with acetophenone. So how do we read this is based on the search score. The higher the score it is, the higher the matching with the reference libraries. Okay, so this is one way that you directly matching with the FDI libraries without need to doing any manual or pick assignations. Okay, but of course, the accuracy of the matching, it depends on how many libraries that you have. The more libraries you have, the more robust, the more comprehensive libraries you possess, then the higher the chances the correct matching can actually occur. Another feature that we have is what I call as multi-search. So multi-search is for components or multi-components analysis. The search function just now is only tells you the major component within your samples. For examples, I have a acetone ethanol mix, okay, in a system. This is just an example. So when I perform, this is the spectrum that I get using the normal scan on ATR. Then I perform a search. Based on the search, as I mentioned just now, it tells me the major component is actually ethanol, but it doesn't detect the acetone since it's a minor component. Okay, this is the spectra, and then the score is 0.7, which is not that high. So from here, we can actually do a multi-search or mixture search, and the multi-search actually can identify up to 10 components, and now it managed to tell me how many components actually in my samples. Okay, it managed to identify ethanol and acetone and the corresponding relative percentage of each component as well. 60% of ethanol, 40% of acetone. Okay, so this is based on the subtraction method. So once it matches a component, the residual spectra will be matched against the library again. Okay, so to match with the next component, and you can do this up to 10 components. So this is good for multi-component analysis. Okay, so search, multi-search, compare, all these are qualitative analysis. You do a searching on it for unknown materials or for quality assurance, quality control of the spectra. So this is AVI, another patented features, which we have methane gas cell, sealed methane gas cell in the instruments. For every scans, it will be referred to the methane gas cell again or internal calibrated again to ensure that the data transferability, okay, or the data integrity. Because like you purchase a cell phones or you are purchasing a car, even though it's the same manufacturer, same brands, different instruments will have different response functions. Okay, for example, different instrument parameters, different accessories of different samples. Okay, so all this is what we call as variations. So with AVI, we can minimize all these variations across different instruments or different units of IR basically. Okay, so we apply a corrections to the spectra. Okay, it might sound confusing here. I'll show you the examples. Okay, so we are scanning hydrochloric acids, for examples. Without AVI, it's the same unit. We scan it multiple times. And now you see that even though it's the same samples, there might be a risk at certain scans, it actually shifted. And as I mentioned, you do not want shifting in the spectrum because if you are using it for identifications, it might identify as different functional groups. And imagine if you are using this for quantitation. Okay, you can use IR for quantitation as well based on peak height or peak area. So the area or the height, because we are taking at this wave number, for examples, you are not acquiring the full pictures of it. Of course, the quantitation results will not be accurate. Okay, with AVI calibrations in the instruments, and this is just a software features, one click, and it will perform automatically for you for the subsequent scannings of the spectrum. So now you can see that not only we standardize the baselines of it, and we can ensure the wave number or the positions accuracies of it as well. Okay, so we can ensure the data integrity of the spectrum. Okay, so one example is this is also data transferability. I have the same samples. I scan at instrument A and instrument B, two instrument, two IR basically. So when I overlap the two spectrum or the overlap spectra, it appears highly similar. Okay, but when I subtract it off, instrument A minus instrument B, actually you can see there is some residuals spectrum, and this is the variations caused by different instruments between different instruments. Okay, without the AVI calibrations. So with AVI calibrations, we can actually minimize it down to the smallest, so practically non-existent. Okay, after AVI calibrated for instrument A and instrument B. This is both scan the same samples. When I overlap it together and minus it off or subtracted it, there's literally no residual spectra compared to uncalibrated AVI uncalibrated spectrum. Okay. So this is the benefits of it. Make sure the accurate wave number calibration, standardization of the baselines, and improve the data transfer between different instruments. Okay, as I mentioned just now, is the features that I mentioned is more for qualitative analysis. So this is, you can do quantitation as well. Okay, so in IR quantitation, we have Beer's law or chemometrics. Okay, we call it spectrum quant, the software we are using, but the algorithm we are using is Beer's law or chemometrics. Okay, so Beer's law is absorbance equals to epsilon BC or CL. Okay, so the K is the molar absorption coefficients. C is your concentration, L is your path length. Okay, so increase concentration, increase absorbance, increase path length, increase absorbance, as I've shown using the liquid cell just now. Okay, so normally for this, similar like what you prepare for your UV, you need to have a standards, a series of standards with different concentrations. Then the signals or the absorbance should increase directly proportional to your concentration, and your R square should be close to 1 for the calibration curve that you plotted. Okay, then the calibration can be used to predict unknown concentration for the samples. Okay, so of course, the prerequisite for using IRS to build a calibration curve is you have to fulfill 3 requirements or 3 criteria before you use Beer's law. First, the peak that you choose must correspond to the components that you want to quantitate. Okay, for example, if you want to quantitate aldehydes in carboxylic acids, so you choose the peak that only coming from aldehyde, not from the carboxylic acid. That means the peak that you choose should not be interfered by other components within your samples. That's one. Second thing is the signal must be increased with increased concentration. Okay, so you can see increase with increased concentrations. Then the third one is the peak that you choose or the signal that you choose must be isolated. This is isolated. This is not isolated. So this is what we call as convoluted peaks. That means multiple peaks within the, so this type of peaks you do not choose, you do not use it for quantitation purposes. Okay, so Beer's law, the limitation is more suitable for relatively simple metrics or relatively pure components. Okay, because once you have a mixtures, if they have the same functional groups, then most probably you can't use Beer's law to build your calibration curve. So of course, standards for calibrations with known concentration, what I have here is the triethyl amine, TA. Okay. So we can build the calibration based on area or height, okay, or even ratio. So you can build your calibration based on this criteria after you choose the corresponding peaks or the corresponding signals. So this is the calibration curve. So we can use this to quantitate or to quantitate unknown samples for this series of samples. Okay. So you can build your calibration based on peak area or peak height. Then we have a more advanced approach, what we call is a chemometric approach, is based on principal component analysis. You have 2 types of algorithm that you can choose from. One is PCR plus, principal components regressions, or PLS1, okay, partial least squares. So these are based on principal component analysis, which is statistics. Okay, so the benefits of this since it's statistical distributions, that means you do not need to identify isolated peaks that responds to different concentration. As I mentioned just now, you can choose overlapping regions in your spectrum or the whole range of your regions if you need from your data, and it's generally suitable for different types of techniques, whether it's mid-IR, near-IR, Raman, or other data types as well. Okay, but of course, since it's based on statistical distributions, the standards that you need to prepare is much larger populations compared to the Beer's law. Beer's law, normally you use only 5 or 7 standards, but for statistic or principal component analysis or chemometrics, you need to at least like 50 standards with different concentrations. Then you build your calibration curve. Okay, so as per usual, input your standards and your concentrations, corresponding concentrations, then choose what are the algorithms that you want to use, whether it's PLS or PCR. These are all chemometrics. So after that, you can use, if you need, you can even use the full range, okay, to build your calibrations. Choose the range, then build your calibrations. So I mean, for quantitation, in the end, for spectroscopic technique in general, if you want to do quantitation, you need to build a calibration, regardless what type of analytic techniques we are talking about, whether it's molecular spectroscopy, for example, IR and UV, or atomic spectroscopy, for example, AA, atomic absorption, or ICP, or OES, optical emission spectroscopy, or ICP-MS. Okay, so all this you need to build a calibration curve for quantitation. But for IR, you have the option to use Beer's law, means based on area or height with the corresponding peaks, or you can use statistical distribution, what we call as a chemometrics approach or principal component analysis. Okay, and this is more of the advanced features that you can do with IR. So we can, since IR is more for identifications, okay, so we can use IR to check for adulterants or impurities. And for adulterant checkings, we have 2 types. One is the targeted and one is the non-targeted. Okay, targeted means we already know what are the adulterants or impurities we are detecting. So we're focusing on that and we want to know how much. Okay, and for non-targeted, we have no idea what are the adulterants or what are the impurities. We just want to screen whether the sample has been tampered with. Okay, so I'm going to show you the examples. Okay, so as I mentioned just now, we can use compare first. Okay, you can scan 2 samples and then you can compare it with a reference, and then you can compare how similar between the compare spectrum with the reference spectrum. And we can set what is the correlation. Means if it's more than 99 or it's more than 98, then we consider it as pass. But for this is very primary, I would say. Okay, because for any small adulterants, if it doesn't generate a strong signals, most probably it won't reflect in your spectrum. So it will appear similar, although it has been adulterated. Okay, so normally this is the primary way that you can use compare to see whether it is similar or whether there's any impurities presence. Okay, but this typically works for impurities with high enough concentration to be detected. If it's not, then it will appear similar and it will pass your compare test. So another features that we have for non-targeted approach, we have what we call as SIMCA, self-independent modeling of class analogy. It's based on principal component analysis as well, or multivariate, if you will. Okay. So for examples, as you can see from here, when we scan the spectra, even though I know that it's been contaminated with adulterants, this is what we call as 1D IR, one-dimensional IR. If you just scan IR as normal, the spectra that you obtain, this is what I consider as 1D, one-dimensional. So from the spectrum that I obtain here, it doesn't show any significant changes or significant dissimilarity between different samples. Okay, but when I subject to the multivariate models or the SIMCA models that I mentioned just now, it's separated based on different sample populations. So different sample group corresponds to differences, even though in the 1D spectrum, it does not show any significant changes. But using the SIMCA algorithm, we can actually separate into different groups. So we know that different samples in different groups have different differences or has been tempered, adulterated with different contaminants or impurities. Okay. Okay, one example is glycerol. So we can send using ATR as like shown here. Okay, one drop here. So of course, if the glycerol usually will be contaminated with all these contaminants that you do not want to presence in your glycerol samples. This is for food safety. Okay, I mean you do not want methanol, for example, or propylene glycol. This is the pure spectrum for the pure components or the pure contaminants. Okay, if the concentration high enough, of course, it will reflect in your spectrum in the glycerol. But typically, the contaminations or the impurities is less than 2%. It's very, very small. Okay. So as you can see from here, even though you have up to 1% of adulterants, most of the spectra still appears highly similar. Okay. So if you use compare functions, you wouldn't detect what's the dissimilarity. It will shows you high correlation or high similarity between different spectra, even though it has been contaminated with different adulterants. Okay. So using the SIMCA algorithm, now it managed to separate whether the sample has or has not been adulterated by the contaminants that I've mentioned just now, the glycerol samples. So this is the uncontaminated or unadulterated. And here is the sample that has been contaminated, whether like, for example, like ethylene glycol, diethylene glycol just now. So SIMCA can separate, even though it's highly similar in the primary spectrum, okay, then you still can manage to separate at even low concentrations what sample has been adulterated or what sample has not. Okay, but SIMCA is for non-targeted approach. Okay, so and then we can do targeted screening as well. So for example, one good example is the milk powders. Okay, melamine. Okay, melamine is contaminated in the milk powders. Okay, to increase the nitrogen content, but this is a systemic disruptor in human bodies. Okay, so it has disrupt your nerve functions and also your hormonal functions as well. So you do not want this presence. So they want, when they add in this, they want to increase the nitrogen content for the milk powders. But actually, this is a highly toxic material, so you do not want it to be inside the, for example, milk powders. Okay, so of course, like for example, melamine at high enough concentration to be detected, it has totally different spectra compared with the milk powder. So from here, we can safely identify whether presence of melamine or not. Okay, but of course, now we want to know how much is melamine presence in the milk powders. So from the peaks that we choose just now, or this region, we can build the calibration curve, and then we can quantitate based on the scan, the spectra. Then we can quantitate how much of melamine is present in the samples, in the milk powder sample. Of course, the standards you have to spike using the spiking techniques, internal standards. You spike with known concentrations of melamine to build the calibration curve. Okay, so calibration can be built based on the PLS just now, okay, the chemometrics, okay, or the principal component analysis. So we have another approach that combines targeted and untargeted approach into one single software, what we call as adulterant screenings. Okay, so not only we can tell what are the adulterants present, we can also tell how much of it is present within your samples. So the way to do this is, okay, this is how you analyze your spectrum. First, the conventional way is, of course, depending on the sampling technique, regardless of the sampling techniques, what we get is the 1D spectrum or spectra. Okay, whether it's transmission or it's reflectance, it's all 1D. Second derivative means from the 1D, we can do a derivations on the spectrum, okay, to separate the overlapping peaks or to identify small transitions or small changes in the spectrum. Okay, the software can goes up to fourth order derivations. But of course, the higher derivation you proceeds, the higher the noise level it will be. And we have the new technique is what we call as 2D IR. Okay, it actually is not that new, but we have what we call as two-dimensional IR, means using, so we can provide more details in the sample informations where 1D spectra is not able to provide. Okay, and then you can generate the spectra in 2D. Okay, we can introduce the perturbations either by temperature, pH, pressures, and then we can see the changes occurring in the IR spectrum.
Sorry to interrupt, Dr. Uy. You
Yep.
have 5 minutes left. Okay,
Sure.
you need to wrap
Yeah.
in 5 minutes. Thank you.
Yep. Okay, so this is, as I mentioned just now, this is the adulterant screen. So we can scan the adulterants inside, and then based on the samples, the adulterant software will tell you what is the percentage presence in your samples for the corresponding contaminants or the contaminants or the adulterants. Okay, so you can detect, and is lower level compared to what is being able to detected by the SIMCAS software, higher sensitivity. Okay, so for 2D IR, I'll go too fast. So we are introducing temperature, pressure, pH, or chemical perturbations to the system. So that's why it's called two-dimensional compared to the 1D that you normally scan. Okay, so for 2D, the spectra, what you will get is what we call as the synchronous plot, asynchronous plot, and also the auto peaks. So auto peaks means the similarity of the functional groups. So synchronous, asynchronous. So you compare between two, how you read the 2D IR is you cut at the center here, you compare for the two samples, the similarity and the dissimilarity. So synchronous show you the similarity, asynchronous shows you the dissimilarity. I mean, for these samples, I'm introducing temperature perturbations. Okay, so go through this. So you have the corresponding accessories as well. Okay, one example, gelatin. So both look very similar, whether it's halal or the bovine, halal gelatin and the bovine gelatin. Okay, bovine and halal. If you scan it 1D, it appears highly similar. Okay, so we want to know what is the difference. Even, and then we do a second derivations. Okay, the process is like this. So from the derivation, nothing much has been changed, highly similar as well. So based on the synchronous, shows the similarity between the bovine gelatin and the halal gelatin. So you can see that the more intense the color means the more changes it occurs at this particular wave number. So it has the similar region, means highly similar. Okay, even the asynchronous shows it to be quite similar in the target, in the region of specifics as well. Okay, for the bovine and halal, that for this, then we can conclude that halal gelatin, the bovine gelatin can be used as a replacement for the halal gelatin. Okay, so you can generate for each of the point that you see here, you can generate a spectrum. Okay, so this is what we call as 2D. Okay, another one is the cosome leaves. So based on the, even though it's the same cosome leaf, but different geographical area actually affects the plant differently as well. So the synchronous plot, it shows differences. Okay, then the auto peak generated, you can see that it has different functional groups. Okay, different spectra. So asynchronous also show differences. So 2D IR is good for differences, or means it's still for identifications, which the 1D IR or the normal IR, you can't identify. So you can use the 2D IR approach to identify what is the similarity or the dissimilarity. I think with that, I'll end my presentation. Thank you very much. So this is the conditions. Okay. Any questions?
Interesting, isn't it? So, okay, thank you very much, Dr. Uy, for a very insightful talk. So I think some of the participants are quite, eager to ask questions.
Sure.
And let me read out the first questions from the chat box for Dr. Uy.
Oh, yeah.
Is there any differences in the IR absorbance or transmittance if the sample used is too thick or too thin? And this is referring to the ATR.
Yeah. Okay. In terms of ATR, since I mentioned the penetration is only 2 microns, so thickness is not factors that you should consider in terms of reflectance, normally we don't consider thickness. Okay, so since the penetration is only 2 micron, hence it's just a surface analysis. So typically regardless of the thickness, you can just perform it as it is. So when we are talking about thickness or refractive index, we are talking about transmissions. So especially like you're preparing pellets. So it's a good way that the pellets that you prepare shouldn't be too thick and it should be transparent or translucent so that the infrared can pass through. If your sample is opaque, the thickness is too thick, the light might be reflected and you will get a very bad quality spectra. And when I mention bad quality spectra is the transmission percentage is lower than 40%. Okay, means the highest point that will from your baseline down to the lowest point of your spectra. So it should be more than 40% to be considered as a usable spectrum, basically. Okay, so thickness is more for transmission, not for reflectance. In terms of ATR, regardless, it's just a surface analysis. So thickness doesn't concern unless you want to do multi-layer analysis. So ATR is not a good tool to do that. Okay, multi-layer, you need to do a cross sections, and best way is to do IR microscopes. Thanks.
All right, so I will invite the participants to ask questions if they have. You can unmute or
I have question for Dr. Oi.
Yes.
Because it's very interesting. Your regarding on the software,
Yep.
Dr. Oi, the SIMCA, is it the latest one from the FTIR? And that's one thing. Second thing, the 2D's result
Yep.
means that if let's say we have the FTIR instrument. So right now at PPSD we have the Perkin. So I don't know this is the which version, but if we would like to have the software to generate the result using the 2D, is it possible for our machine? Let's say if not for the from the latest instrument. Thank you.
Yeah. Okay. SIMCA is actually not new. Okay, it's algorithm based on principal component analysis. So mostly it's for discriminations of sample that is or spectra that is highly similar, or for sample that you suspect that's has been tampered with or has impurities inside, which from the normal scannings that you can't see. Then you can use SIMCA for discriminations or discerns, like what I've shown just now. As for 2D IR, is what is more important is you should have the corresponding accessory. Let me show the accessories. Okay, so you should have this what we call as the variable temperature solid sample cells. So the 2D IR software is an additional software. It comes together with a set of these accessories. So you need to, because it's a transmission methods and we are introducing temperature as parameters. So if you're running solids, you need to press into KBR and then lock it into the sample holder like this and put into this temperature controller jacket. Okay, what we call as a jacket cell holder, and then you control the temperature under a control heating rates. Okay, then you scan at different temperature what is the different spectrum generated or different spectra generated. Okay, and then using the 2D IR software, it will give you the synchronous plots, the asynchronous plots. Okay, so all this is coming from the software, but you must have the accessories ready first. And the models that you have is since it's using its own software and its own accessories, so it does work with your IR as well, regardless of the. I mean, 2.0 doesn't works, but the one that you have shown, I think is the frontier unit, it does work. So this is for liquid samples. So we have different types of cells for different types of samples as well. And this is the results that you will get, what we call as a synchronous plot, the asynchronous plot, and the auto peaks based on the different point that you want to generate. Or if you want to see, for example, what spectra is being generated here, then it will generate for you. So yeah, I mean, it works with your instruments, no worry.
Thank you, Dr. Oi.
Thank you.
sorry, let me remind the participants, please just log into the link that we have provided in the chat box for your attendance and feedback. Okay, at this stage, there is any more questions from the participants?
Hi, Dr. Oi.
Hi.
I'm Zura. This question from an amateur in FDR. As you mentioned about noise in your presentation just now, so what causes noise in FDIR and how to reduce the or troubleshoot the noise? Do we have to look on the instruments first or our sample spread? So what is the most contributing factor? Do you have any suggestion?
Yep. Okay. So when you have generated a spectrum, means basically that's pretty much what you can do. So the most important thing is first you need to use the right tools or the right accessories. Okay. If, for examples, if you are using solid transmission, means the KBR method, that means your samples shouldn't be too thick and it shouldn't be opaque. So this is the criteria. So if it's liquid cells, liquid samples, it shouldn't be too concentrated or too dilute. So this also will generate a lot of noise as well. Then if you're using ATR, as I mentioned just now, if you have ATR, you run solids, you should make sure that the sample has a good contact with the crystals, okay? And then for solids, for liquid, you can just one drop on it. But okay, now, if you are very sure that your sampling tools is the correct tools, however, you still get a lot of noise in your spectrum. Now you have to look into your sample characteristics, because as what Dr. Fatiha mentioned, different functional groups have different vibration intensity or the absorber intensity that reflects into your spectrum. So it can be strong, peak, medium, or weak. Okay, so might be your sample typically or generally will have a weak absorptions. Thus, it increase the noise levels as well. For examples, if you are using ATR diamond, but you're running like carbon nanotubes, graphene graphite, you typically will get very, very weak intensity because most of the infrared has been absorbed by the samples. So not much light being reflected into the detector, hence a lot of signal to, a lot of noise and generally weak signals. Okay, you understand that signal not a relative um, ratio. That means if you have good signals, typically you will have low noise levels, okay? And as I mentioned, if you want to reduce the noise from the software point of view, then you can increase the number of scans or you can use a larger resolutions. That means 8 cm minus 1. So you can use this. But generally, I wouldn't adjust from there. Typically, in terms of IR, we always look at the sample preparations first or the sampling tools that you're using and how you prepare your samples. Yeah. And if worst come to worst or there's nothing else that you can do, then you increase the resolutions or you increase the number of scans. So this is what you can do. So because IR is very flexible too, so these are the things that you can optimize for your samples.
Okay, thank you so much, Dr.
Thank you.
Okay, I have one. It could be like a silly questions. I'm thinking of bone. Let's say if you want to analyze bones or tooth samples, you want to look at brittle bones disease, for example. Which one is the best way to just cut the bones into specific size, or you have to make it into powder, or how does it?
Okay,
in
when we
sense?
are talk about bones, normally, I'm not the bio people. I would guess most of it is phosphate based materials, orthophosphates or photophosphate based. So these
Yeah,
are
phosphate,
generally
calcium.
inorganics and calcium as well. So these are generally inorganics. Okay, even though its covalent bonded is oxide, for example, still these are mostly inorganic. So typically weak signals. So I wouldn't recommend you are using ATR because first, the sample might not be homogeneous. And since it's just a surface, you might not get a very good spectra. So I would still recommend you crush it and then you scan it using the transmission methods, mix with KBR and then scan it as using transmission. But the best way is you mix it with using 5IR, since 5IR is good for inorganic materials. Okay, so 5IR because it's good for metallics or ionic bonding. So it has to mix with polyethylene powder. And that's another techniques. Yeah, for inorganic. But of course, you can use mid-IR to scan, but most of the inorganic will have absorptions at 550 to 450 wave number, which is towards the end of the spectrum already. So not much information. So for inorganic, typically it's 400 and below. So I would recommend using FAR or Raman if you have that. But Raman, of course, is more for checking defect sites or acid sites or basic sites. So yeah, FAR will be a better choices.
Awesome. All right, so it's lunchtime. I think everyone is excited for the, lunchtime, the lunch meal. So thank you very much for participants. Thank you
Actually, I
very
want
much
to thanks
for the Dr. Oi speakers.
Dr. Oi
Yep.
has because we are from the same UTM, so my pleasure, really happy to have you in our talk today. So hopefully for the
Thanks for having me.
next maybe we going to have some event on the FTIR. So hopefully you can join us again, Dr. Oi.
Sure.
Okay. Can we please give big round of applause for both of the speakers today so that we can end this session?
Thanks, everyone.
Okay.
Very much.
Thank you very much for joining us today. We are very glad for you to join us as well, and hope the information you get today will help you, the knowledge will help you for your research, for your studies. All right. Thank you very much, everyone. Have a good day.
All right. Thank
Thanks,
you.
everyone. Bye.
Bye.
Take care.